Part 1. Introduction to Intraoral Digital Radiographic Imaging. This video was created to provide an overview of intraoral digital imaging. The objective of this module is to provide the learner with an introduction to intraoral digital radiography using the paralleling technique, SCHC digital sensors, and XCP instruments. What is digital imaging? It is an electronic sensor with specialized software which transmits an instantaneous image to a computer monitor. There are two methods of digital image capture. One is direct capture using solid-state sensors. A second method is indirect capture, which includes the phosphor plates, although some sources categorize phosphor plates as direct capture, and scanning of film images. Digital imaging has some similarities with film technology. Radiation is used in both technologies, and the capture is intraoral. Paralleling technique can be used as well. Digital images will provide the same but not more information than film technology. There are differences in digital imaging also. Digital imaging uses a different type of receptor and captures the images differently than film. Less radiation is needed because the receptors and sensors are more sensitive to radiation. Also, the sensors can capture the images more rapidly. This table displays the differences in radiation doses among different modalities, including film, plates, and solid-state sensors. Sensors reduce the radiation dose by 50% or greater. Film images are similar to a painting and display as continuous spectrums of gray shades. Film-based imaging is based on emulsion, which contains silver halide crystals suspended in gelatin, whereas digital sensors have orderly rows and columns of pixels. When exposed to radiation, electronic charges are produced on the surface of the sensor, which is digitized and sent to the computer software. Digital sensors are similar in design to a mosaic. They are composed of pixels arranged in a matrix of rows and columns, aligned to represent the intensity or gray level of the image. Digital imaging includes a hard sensor or phosphor plates. An analog to digital converter is required, which helps the computer organize the pixels in their correct locations and displays shades of gray that correspond to the number that was assigned to a voltage signal. In the digitization quantization process, each square of the pixel grid is assigned to numbers which determine the location and density of the area. In direct digital radiography, the radiation strikes the sensor. The analog image is converted to a digital image and transferred to the image software, which is then displayed on the monitor. This is just another image showing the process of digital capture. To restate, a value is assigned to each pixel that represents the gray level of the image. Then the software organizes the pixels and displays the density of the object via multiple shades of gray. There are several types of solid-state sensors. The basic component of the sensor includes a back housing and cable, an electronic substrate, the chip, a fiber optic faceplate, the scintillator screen, and the front housing. One type of sensor design is known as a CCD, charge-coupled device, which is the electronic circuit inside the sensor. The chip detector converts the X-ray photons into electronic charges. Electrons are deposited into the pixels. The pixels provide multiple shades of gray. Image capture occurs in this manner. Radiation strikes the sensor. Electrons released from the silicon. This produces an electronic charge. Each pixel, referred to as an electronic pixel well, contains a charge proportional to the number of electrons that reacted within the well. Each well corresponds to a specific area on the computer screen. This is now the electronic latent image and its formation. A second type of sensor is a CMOS, complementary metal oxide semiconductor, and the CMOS APS. The CMOS is sensitive to light and provides small details in the X-ray image by isolating each pixel from its neighboring pixels. Similar to the CCD, electronic hole pairs are generated within the pixels in relation to the amount of X-ray energy that is absorbed. This charge is transferred to the transistor as small voltage. The scintillator screen inside the sensor converts the radiation into visible light and guides the light through a microcolumnar structure. Fiber optics transmit the light to the surface of the sensor, allowing a high signal-to-noise ratio, resulting in detailed images. CMOS produces higher visible resolution. CMOS chips have a smaller pixel size, require less power, cost less to produce, and use a USB connection. There are a variety of solid-state sensors available in dentistry. Most sensors are wired. The wire limits the clinician's range of motion and requires infection control procedures that include the cable as well as the sensor. What we don't often realize is that the active area of a sensor is smaller than the actual size of the sensor and is definitely smaller than film. The red text in this image displays the outer size of a number 1 and number 2 Schick sensor, and the blue text lists the actual viewing area, which is quite smaller. The smaller active viewing area has implications for the sensor placement for the clinician. So while you believe you have positioned the sensor to capture areas such as the apices, the dead space of the sensor may display an absence of apical coverage. Gendex, Dexis, and Schick Sirona are 3 of the most popular brands of sensors. You can see that dimensions, thickness, number of pixels, resolution, and costs vary. Schick sensors have the highest number of pixels and resolution, which contributes to a sharper, more defined image. You can also see there are differences in shapes and size. Dexis has only one sensor with beveled edges that many clinicians find easiest to use. Schick has 3 sizes, a 0, 1, and 2. Gendex has 2 sizes with rounded edges. This is another view of the 3 sensors showing the backside and thickness of each sensor. These are the specifications of the Schick sensors, but these change with each new sensor version. Dexis and Gendex sensors plug directly into the computer USB port, whereas Schick requires the sensor to be plugged into an interface module, which plugs into the computer USB port. This concludes the overview of intraoral dental digital imaging. Techniques specific to Schick and EagleSoft will be presented in lab. If you have questions, please bring them up in class. Thank you.